Today, we're going to forge a new understanding of a material that is, well, literally all around us: cast iron. We're going to break down how engineers pick the right type for the job, and, more importantly, why the most obvious choice can often be the absolute wrong one.
So let's just jump right in with a puzzle, one that honestly stumps a surprising number of engineers. Picture this: a part made from a really high-strength cast iron fails, just breaks, and it fails under totally normal operating conditions. Now, on paper, it should have been way more than strong enough. So what on earth went wrong?
And this isn't just some textbook thought experiment, it really happens. Failures like the one you see here are a real-world problem, and they point to a huge but super common mistake in how we select materials. It's a mistake that starts way before any metal even gets melted.
That mistake? Well, we can call it the intuition trap. It's this simple and, pretty compelling idea that the biggest number you see on the spec sheet, usually tensile strength, must equal the best performance. We just see stronger, and our brain immediately jumps to better.
But here's the thing. Engineering doesn't happen on a datasheet. It happens out in the real world, where you've got vibrations and heat and all sorts of complex stresses. In engineering, context is absolutely everything. A material's real success depends on a whole bunch of different properties all working together, not just one flashy headline number.
So to really understand how to avoid this trap, we got to meet the main players in the cast iron family. See, it's not just one material. It's more like a family of specialists, and each one is defined by its own unique internal structure and its own special set of talents.
Okay, so you're most likely to run into gray iron and ductile iron, but there are other key players too, like white iron and compacted graphite iron. And it's so important to get this. This is not a good, better, best situation. Not at all. Think of them like specialized tools in a toolbox. You wouldn't use a hammer to drive a screw, right? Same idea here.
And this is where it gets really interesting. A tiny, tiny change at the microscopic level creates this massive difference in how the material behaves. Let's just compare the two most common ones, gray and ductile. It really all comes down to the shape of the graphite that's inside the iron. So in gray iron, the graphite forms these sharp little flakes. Now these flakes are amazing at soaking up vibrations, which is a huge plus sometimes. But they also act like tiny built-in cracks, which makes the whole material pretty brittle. Now, contrast that with ductile iron. Thanks to some clever chemistry, the graphite forms little spheres, or nodules. Because they're round, they let the metal around them stretch and deform without breaking. And that's what gives ductile iron its signature toughness. It can bend where gray iron would just snap.
Okay, so we've got all these different specializations. How in the world do we actually choose the right one and not fall into that intuition trap? Well, what we need is a system. A framework that forces us to look beyond just one number and really think about the whole job the part has to do.
And here it is. This is the engineer's gauntlet. It's so powerful because instead of just asking which one is the strongest, we're asking a whole series of questions. We have to ask, does this part need to absorb vibration? Will it get hit with sudden impacts? Does it need to resist being worn down? That's where something like white iron, which is incredibly hard, just shines. Think about liners for a cement mixer. We also have to ask, how easily do we need to machine it? And, what's the budget? Sometimes you need something in the middle, which is where you get compacted graphite iron, perfect for things like high-performance engine blocks that need a balance of strength and damping.
All right, let's put this framework into action. We're going to go all the way back to our original puzzle, that high-strength part that failed. Now we can use our gauntlet and see exactly what went wrong.
The process is actually pretty straightforward. First, you define all the conditions, not just the one main load. Second, you just get rid of any material that's a total mismatch for the most important condition. Third, you weigh the trade-offs between what's left. And finally, you pick the one that gives you the best overall balance for that specific job.
So here's the solution to our puzzle. The failed part was a machine bed. It was subject to constant vibration. The engineer chose ductile iron because it had great tensile strength. They fell right into the intuition trap. But for this job, gray iron, even though it's technically weaker in tension, was the far superior choice. Its ability to dampen vibrations was the most critical property, making it way more durable and reliable in that specific context.
And this is just a brilliant illustration of why the most important information is not always that big number on the front of the datasheet. A material's true performance is really written at the microscopic level.
Don't just take my word for it.
Researchers in this field point this out all the time. You just can't guarantee how a material will perform by knowing its chemical recipe. You could have two pieces of iron with the exact same chemical makeup, and they could have wildly different properties.
The real properties are decided by so many other things. It's about the shape of that graphite we talked about. It's about the structure of the metal matrix around the graphite. It's even about how fast the casting cooled down in the mold. For instance, if you cool it too quickly, you can make it super brittle, even if the chemistry was perfect. It's all these little details working together that define how the material is actually going to behave.
So what's the big takeaway here? Optimal selection is never about finding the single best material out there. It's about deeply understanding the engineering challenge and then choosing the right set of trade-offs. It's a fantastic reminder that sometimes the strongest option isn't actually the most resilient one. So I'll leave you with this. What's an obvious choice in your world that might be worth a second, deeper look?